Hello everyone, welcome to the video lecture series on circuit analysis. In the last session, we have seen the very important terms, nodes, branches, and loops, which are important for circuit analysis. So today we'll see examples how we can determine the number of nodes, branches, and loops. So as you can see, for the given circuit, how many branches, nodes, and loops are there. Okay, branch is the components of the circuit, components or device connected in the circuit. So we can have this is the first component. So this is component 1, this is component 2, and this is component 3, component 4, and component 5. Okay, so totally we have 5 number of branches. We have 5 number of branches. And to determine the number of nodes, you can see here component 1 and 2 that are connected at point A. So point A is a node. This is a node which is used for connection of component 1 and component 2. And at point B, component 2, 3, 4, and 5. Point B, that means 2, 3, 4, and 5. They are connected at component B. At point C, component 1, 3, 4, and 5, they are connected at point C. So totally we have 3 number of nodes. Okay, 3 number of nodes. So to determine the loops, we can redraw the circuit. That means this one is component 2, okay, component 3, component 4, component 5, okay. So plus minus, we have this, okay. So this is 5 ohm, this is 10 volt, and this is 2 ohm, 3 ohm, and this one is 2 ampere. Okay, we have total. So let's consider this point. This point is A, B, C, D, E, F, G, H. Okay, so let's consider the loops A, B, C, D, E, F, G, H. This is one loop, and it is a dependent loop because it has loops inside it, and the other one is loop ABC, F, G, H, A. There is also A. This is another loop. And the other one is A, B, G, H, A. This is another loop. Okay, this is another loop. And the other one is B, C, D, E, F, G, B. This is another loop. Okay, this is another loop. And the other one is C, D, E, F, C. This is another very important loop. Okay, and the other one is B, C, F, G, B. Okay, so totally we have 1, 2, 3, 4, 5, 6. We have 6 number of loops. Okay, 6 number of loops for this circuit, okay? So it's better to represent the nodes so that it's very clear to determine the number of loops in the circuit, okay? And we have three independent loops. Okay, we have three independent loops. That means we can consider A, B, C, G, H, A. This is one independent loop, and the other one is B, C, F, F, G, V. Okay, this is another independent loop, and C, D, E, F, C. So we have three number of independent loops. Independent loops means a loop which does not have any loop inside it. Okay, so we can check that the number of branch which is equals to L plus n minus 1, where L is the number of independent loop, n is the number of nodes, and B is the number of branches. So we can have 5 is equals to 3 plus 3 minus 1, which is equals to 5. Okay, which is equals to 5. So that's how we can determine the number of loops, the number of nodes, and the number of branches. When we come to Kirchooff's law, this is the second very important fundamental laws. We have two laws for Kirchooff's law. That means you can consider KVL and KCL. Okay, this is second law. Of Kirchooff's law, and this is the first law of Kirchooff's law. So Kirchooff's current law states that the algebraic sum of current entering a node or a closed boundary is 0, or the sum of currents direct toward this or to the node or is equal to the sum of the current directed away from the node. So, or totally, the sum of the current entering a node is equal to the sum of the current leaving the node, the same node. So as you can see here, we have 5 number of branch currents. And as you can see, the 5 branches are connected at this point. So this is the point where KCL to be applied. So as you can see here, I1, I4, they're entering the node, and I2, I5, okay, I5, they're leaving the node. That means I3 also entering the node. So Kirchooff's current law states that the sum of the current entering the node is equals to the sum of the current leaving the same node. So as you can see here, I1, I4, and I3, they're entering the node, and I2 and I5, they're leaving the node. Okay, leaving the node. So you can consider here. So KCL states that I1 plus I4 plus I5, which is equals to I2 plus I2 plus sorry, this one is I3. This one is I5. So this is sum of current entering. Okay, and this one is leaving. Okay, so the sum of the current entering the node, which is equals to the sum of the current leaving the node. So as you can see here, this one is a closed boundary. This one is a closed boundary. Okay, this is a closed boundary. Okay, this is a closed boundary. So this current, it is entering the boundary, Okay, this is entering the boundary. This one is entering the boundary. So for this closed loop, that means for this closed loop, the sum of the current at this closed loop will be 0. And this is also another closed loop. So again, we can consider a closed loop can be considered as a single node. Now, using Kirchooff's law, let's consider determine the current I for the circuit shown in the figure below. So we can consider this is a closed loop. So we can write the sum of the current entering a closed loop, which is equals to the sum of the current leaving a closed loop. Okay, a closed loop. So the closed loop can be considered as a single node. Okay, so you can see here 2 ampere minus 3 ampere are entering the closed loop. Okay, 2 ampere, you can consider 2 ampere and minus 3 ampere, they are entering the closed loop, entering into the closed loop. Okay, and the other one is 4 ampere and I, they are leaving the closed loop. So we can determine using KCL 2 ampere minus 3 ampere, or I can write 2 ampere plus minus 3 ampere, which is equals to 4 ampere plus I. Okay, plus I. So minus 2 ampere minus 3 ampere is equals to 4 ampere plus I. So minus 1 ampere, which is equals to 4 ampere plus I. So I should be equals to 4 ampere minus 4 ampere minus 1 ampere, which is equals to minus 5 ampere. So using this, we can determine the current on the closed loop. Okay, on the closed loop. The second law states that which is Kirchooff's voltage law, so states that the algebraic sum of all voltage around a closed loop or has is zero. So as you can see here, we have the voltages in the component. For this circuit, we have sources, which is two independent sources. So you can consider this a closed loop. So as you can see here, all the components are connected in series. So the value of the current will be constant. So mathematically, KVL states that the algebraic sum of all voltages around a closed path will be 0. Okay, so using this, we can consider, for example, V1 minus V1 plus V2, okay, plus V3, okay, minus V4, okay, plus V5, which is equals to 0. So this is summation of voltage. This is summation of Vn, where n runs from Vi runs from 1 up to n is equal to 0. Okay, so this is how the KVL states how the KVL states. So I can write this one. V1 plus V4, which is equals to V2 plus V3 plus V5. Okay, V5. So as you can see here, V1 it is for the loop direction, that is raised from negative to positive. V2, V3, and V5 in the loop direction, they are moving from positive terminal to negative terminal, positive terminal to negative terminal. And for V4, for the loop direction, it's moving from negative terminal to positive terminal. So when we are moving from negative terminal to positive terminal, it is voltage rise. We call it voltage rise. When we are moving in the loop from positive terminal to negative terminal, it is a voltage drop from high potential to low potential. We are moving from high potential to low potential, so that is a voltage drop. That's a voltage drop. So generally, we can say that the sum of the voltage drop is equals to sum of voltage rises. Sum of voltage rise. So this is the sum of voltage rise. Okay, rises, and this one is the sum of voltage drops. Okay, the sum of voltage drops. So we can consider just like this: the sum of the voltage drop is equals to sum of voltage rise. Okay, so we can, around the loop, we can take the voltage rise as negative and voltage drop as positive, or we can reverse. That means when we are moving around the loop, we can take voltage rise as positive and voltage drop as negative. Okay, so that will be very easy when we are applying KVL. So let's consider applying the KVL equation for the circuit of the figure below to find the current I. The current I flowing through the stress-connected elements. So let's consider this loop. This is a closed loop. So let's take the voltage rise as positive. Take this solution. Take voltage rise as positive and voltage drop as negative. Okay, negative. So we can apply KVL. So apply KVL to find the current I. So we can take VA minus V1, okay, minus VB minus V2 minus V3, which is equals to 0, Okay, so VA minus VB, which is equals to V1 plus V2 plus V3. Okay, from Ohm's law, V1 is R1 I, V2 is R2 I, and V3 is R3 I. So let's substitute VA minus VB, which is equals to I into R1 plus R2 plus R3. Okay, so from this we can write I is equals to VA minus VB over R1 plus R2 plus R3. Okay, so the current can be determined by using this, just by applying the KVL application. So it says that find V1 and V2 in the circuit given below. So we can apply KVL to the loop since all the elements are connected in series. So the current is constant. The current is constant. So let the current be I. So we can take the voltage rise as positive, okay? 10 minus V1 plus 8, okay? Plus 8. So minus V2, which is equals to 0, which is equals to 0, okay? So 10 plus 8 is 8, which is equals to V1 plus V2, V1 plus V2. So what's V1? Just by applying Ohm's law, okay, which is 4I, and V2, which is 2I, okay, just by applying Ohm's law. So let's substitute. AT, which is equals to 4I plus 2I, okay? So 80, which is equals to 6I. So from this, I should be equals to 18 divided by 6, which is equals to 3 ampere. So you can consider here, we are asked to determine V1 and V2. So from this, V1 is equals to 4I1, 4I, which is equals to 4 times 3, which is equals to 12 volt. And V2, which is twice of I, which is equals to 2 times 3, which is 6 volt. So this is the answer for V1 and V2. So you can check the KVL. That means the sum of the voltages around the loop should be 0. You can consider, for example, for checking purpose, okay, that means 10 minus 12 plus 8 minus 6, which is equals to 0. 0 is equals to 0. Okay, so that's the principles of KVL. And the other one is find V1, V naught and I in the circuit given below. So we can apply KVL. So let's take the loop. Okay. So which is 12 minus 4I minus 2V naught plus 4, okay, plus 4 minus plus V naught, because we are moving from negative to positive terminal. So plus V naught, which is equals to 0, So what's the simplified expression? 12 minus 4I, okay, minus V naught plus 4, which is equals to 0. So 60, which is equals to 4I plus V naught. Okay, this is equation 1. Let's say this is equation 1. But from Ohm's law, okay, V naught, which is equals to minus 6I. Okay, now this is equation 2. So substitute equation 2 into equation 1. Okay, so we can have 60, which is equals to 4I minus 6I. I is equals to 16 over 2. So which is minus. So you have negative 8 ampere. Okay, negative 8 ampere. So V naught should be minus 6I, which is minus 6 times -8, which is equals to 48 volt. 48 volt. And I is already obtained. That's all for today. Thank you.